Welcome back to Calculus with Mr. Robeson. So this is the last one in 2.3. So we're going to look at derivatives of trig functions that probably involved quotient rules to derive them. We're going to look at position, velocity, and acceleration and how those things are related. Previously, we looked at just position and velocity. And then we're going to talk about some higher order derivatives, just what the notation is for bigger derivatives, for like third derivative and fourth derivative and fifth derivative. All right, so some trig functions. So here are these derivatives. So derivative of tangent is secant squared. This is how we write secant squared. It means this, secant of x times itself, squared like that. Derivative of secant is secant times tangent. Derivative of cotangent is negative cosecant squared. And the derivative of cosecant is negative cosecant times cotangent. So the c's all go to negatives, right? C, negative, C, negative, and the derivative of cosine is negative sine. So all the c derivatives are negative. Now, the way that they're coming up with these derivatives is they're taking something like tangent and they're switching it to sine over cosine. So they're saying that this is sine of x over cosine of x, and then they're doing the quotient rule. And when they simplify, they're getting just secant squared. So if we do this one, derivative of sine of x over cosine of x, using the quotient rule, we get bottom times root of the top. Derivative of sine isn't just another cosine, minus the top, sine, times root of the bottom, derivative of cosine is negative sine, all over the bottom squared. All right, so we get these two negatives cancel out. So we'll get cosine squared plus sine squared over cosine squared, like that. Now, if you remember back to trig identities, cosine squared plus sine squared, we usually say it the other way around. We usually say sine squared plus cosine squared, but that is one of our Pythagorean identities, and that is just equal to 1. So we get 1 over cosine squared, and 1 over cosine squared is just secant squared. Right? Cosine and secant are reciprocals. All right? And that's basically the same thing we're doing with all the rest of these. We're changing them to sines and cosines whenever possible, doing the quotient rule, and that is how we get our derivative rules. So derivative of tangent is secant squared. Derivative of secant is secant again, and it gets another tangent. So tangent and secant kind of go together. Derivative of cotangent is negative cosecant squared, and derivative of cosecant is negative, because it started with a c, cosecant again times cotangent. So cotangent and cosecant kind of go together. So remember, they're the oddballs with the c's. And the Pythagorean identity goes with those two as well, and there's a Pythagorean identity that goes with those two as well. All right, so let's look at some practice here. Derivative of x minus tang of x. So derivative of y we can say is dy dx, or y prime. Derivative of x is 1 minus the derivative of tangent, secant squared. Okay, there's our answer. We can simplify that if we want, or we can leave it like that. Simplifying it would involve using the Pythagorean identities, but that's fine right there. All right, over here, we've got x times cosecant of x. So we have something with x times something else with x. We are doing a product rule. All right, so the product rule says that our derivative is first times derivative of the second. Derivative of cosecant is right here. Negative cosecant of x times cotangent of x plus the second, cosecant, times derivative of the first, which is just 1. All right, now we can distribute here, I guess. Not really distribute, just get rid of the parentheses and bring the negative out front. And really, there's not much else we can do. If you want to pull out a cosecant, you can, but you don't need to. And there's our answer right there. If we want to pull out the cosecant, we can, but that's fine right there. All right. So now, do we remember our derivative rules for trig? All right. If you need to go back, you can go back. Just go back in the video a little bit and look at it. But we want to find the derivative of secant minus cosecant. All right. First up, the derivative of secant. Well, do you remember what it was? I remember secant goes with tangent. Tangent is secant squared. Secant is just secant times tangent. Minus derivative of cosecant. Let's see, cotangent was cosecant squared, negative cosecant squared. This starts with a c, so it's going to be negative. So I rewrite it times cotangent, like that. So these negatives are going to cancel out. And we're just going to get secant of x, tangent of x, plus cosecant of x, cotangent of x. And there's our answer. Now we can try and simplify that more if we want. We can get a common denominator, do all sorts of things, but that's fine right there how it is. And that is an answer choice. That looks like answer choice A to me. So there we go. We're done. It's A. All right, so this guy does not look like fun to me. So we've got 1 minus cosine of x over sine of x. So if we want to find the derivative of that, we could do the quotient rule if we wanted to. But the quotient rule is a lot of work, and we still get a fraction. Let's try, since there's just the one term on the bottom, to divide everybody first. So if we divide everybody first, we have 1 over sine of x minus cosine of x over sine of x. 1 over sine is cosecant. Cosine over sine is cotangent. So now we can take the derivative of that. It's just two derivative rules. The derivative of cosecant is negative cosecant of x times cotangent of x, minus the derivative of cotangent is negative cosecant squared. So these two negatives will cancel out. We'll get negative cosecant of x times cotangent of x plus cosecant squared x. And there's our derivative. We can leave it like that if we want. We can factor out a cosecant if we want, but that's perfectly fine right there. So that's one way to do it. So that's dividing first. Now what happens if we do this using a quotient rule? Well, the quotient rule says it's bottom or low, d high. Derivative of 1 is 0. Derivative of negative cosine is negative sine. So actually, well, derivative of cosine is negative sine. We have another negative, so we'll have two negatives in a row, like that. Minus the top, 1 minus cosine of x, times derivative of the bottom. Derivative of sine is cosine. All over the bottom squared. This is looking much bigger than the other guy. So sine squared. All right, and now we can simplify. Let's see, those two will cancel. Those negatives will cancel. We're going to get sine squared minus, we're going to have a 1 times cosine, so minus a cosine of x, minus negative cosine times cosine, so we're going to have plus cosine squared all over sine squared. All right, so let's see. We've got a sine squared and a cosine squared. We can group those together. And then we still have the minus cosine all over the sine squared. And the whole point of grouping those together is sine squared plus cosine squared is 1. So we get 1 minus cosine of x over sine squared x. Kind of looks like 2x here, but that's squared. All right, and there's our answer. And then you're probably looking at me like, those don't look the same at all. Well, what happens if we just divide each part here? So we get 1 over sine squared minus cosine over sine squared. 1 over sine squared is cosecant. So we get cosecant squared. We can put 1 cosine with sine here. So we can say this is basically cosine of x over sine of x times 1 over sine of x, like that. So we have the 2 sines on the bottom and the 1 cosine on top. Cosine over sine is cotangent. 1 over sine is cosecant. And now it matches. So we got the negative here with that guy is right there. And then this guy, cosecant squared, positive cosecant squared. All right, so higher order derivatives. So the rate of change of velocity is something we call acceleration. So like if we have feet per second and we find its rate of change, then that would be per second. So in other words, that would be feet per second squared, like that. So we end up with the time squared on the bottom, and that is acceleration. All right, so we start with a position function. Usually we use s. Sometimes we use h for height. Doesn't matter. S of t is our position. Its derivative is v, velocity. And then if we take the derivative of velocity, that gives us our acceleration. So that's the rate of change of velocity. That is the second derivative. So that's why we put 2 little apostrophes there, 2 prime signs. That's the second derivative of position. So now we can take higher derivatives. We can just keep taking derivatives of derivatives as many times as we want, really. All right? But it doesn't always have applications, but we can still do it. Because the moon has no atmosphere, a falling object on the moon encounters no air resistance. In 1971, astronaut David Scott demonstrated that a feather and a hammer fall at the same rate on the moon. The position function for each of these falling objects is given by s of t equals negative 0.81 t squared plus 2, where s of t is the height in meters and t is the time in seconds. What is the ratio of the Earth's gravitational force to the moon's? All right, so the Earth's gravitational force, Earth gravity, is the same as its acceleration. And in meters per second, acceleration on Earth is negative 9.8 meters per second squared. All right, to find the acceleration of this guy, we need to take its second derivative. So take the second derivative. There's no trick. We just take the first derivative. So we bring down the 2. We get negative 1.62 t. Derivative 2 is 0. We get t to the first. And then we take the second derivative. So this was velocity. This is v of t. Now to find the acceleration anytime t is the second derivative, which is the derivative of velocity. We don't have to write all this out every time, by the way. It's just negative 1.62. All right, so the acceleration on the moon is not the same as the acceleration on Earth because the moon is a different size. All right, so if we want the ratio of the Earth's to the moon's, that would be negative 9.8 to negative 1.62. And if we were to divide those, 9.8 divided by 1.62, we get it's about 6 times bigger. All right, 6.05-ish. But the Earth's gravity is about 6 times stronger than the moon's gravity, which means you can jump really high on the moon. All right, so an example. Given that the position, s of t, is negative 4.9 t squared plus 20t plus 50 is the height of an object in meters, find the acceleration when t equals 3 seconds. So we need to take the second derivative and then plug in 3 to t. So go ahead and pause it, take the second derivative, and see what you get. All right, so velocity will be our first derivative. We bring down the 2 here, we get negative 9.8 t plus, derivative here is 20, derivative 50 goes away. Next up, our acceleration is the next derivative. It's the derivative of velocity or the second derivative of position. So here it's just negative 9.8 and the derivative of 20 is 0. So we just get that our acceleration is negative 9.8. We're working in meters and seconds. So this is meter per second squared. We don't have to plug in 3. There's nowhere to plug in 3. It's always negative 9.8. And that happens a lot with falling objects. So there's our answer, negative 9.8. All right, higher derivatives. So we finally took our first second derivative and it was double prime. So we can do y double prime like this for our second derivative. Also means the same thing. All right. If we're using the dy dx notation though, it's not dy squared dx squared. It's d squared y over dx squared. This part here works like our operator, and this part here is our function, f of x. All right, so our third derivative, we've just put 3 primes in there. But again, it's d3 with a y on top, and then dx cubed. This means take the third derivative with x as our variable and y as our original function. When we get to higher derivatives, we don't want to keep writing these primes forever. We'll run out of space. So when we get to 4, we usually switch over, and we don't just write 4, we put it in parentheses. That way we don't think it's an exponent. So the fourth derivative is y parentheses to the fourth, or f parentheses to the 4. And same thing here, d to the 4 over dx to the 4th, or so d to the 4y over dx to the 4th. And that works for any higher derivatives, the 5th derivative, 6th derivative, 100th derivative, whatever, doesn't matter. We put the number in the parentheses. Number here, number here. All right, so let's take a look at this guy. Let's find all the derivatives. So the first derivative, the second derivative, the third derivative, and so on. All right, luckily it's just power rules. So the first derivative, we bring down the 3, 15x squared, bring down the 2, 4x, and we just get 8 there. Derivative of negative 10 is 0, so there's the first. To find the second derivative, just more power rules. 30x minus 4, derivative of 8 is 0. All right, third derivative, we're still writing primes. We get 30, and derivative of 4 is 0. Fourth derivative, so now we don't write primes anymore. We put a little 4 in parentheses. Derivative of 30 is 0. The fifth derivative, still going to be 0. Every derivative after that is going to be 0. So for x greater than or equal to, let's see, it started at 4, so we can say for x greater than or equal to 4. So there's every derivative. The first derivative, the second derivative, the third derivative, the fourth, fifth, sixth, and so on are all just going to be 0. That happens with polynomials. All right, so that was a look at derivatives of trig functions, how position, velocity, and acceleration work together, and then higher order derivatives. All right, so that is the end of 2.3. So check out the Google Classroom for the homework assignment.